but we have not stopped. We are just starting. And I tried solving questions with you in the last class. I think that was on Saturday. So on Saturday, I explained a lot of things about magnetic fields. Now, what we explained on Saturday, we want to make use of it now on magnetic field. So we want to look at the force on a current carrying conductor in a magnetic field. So please, let's keep quiet. Some of you are still talking. This is not chemistry. We could have been joking and I was laughing while I was teaching chemistry. There are some subjects that requires high level of seriousness, high level of attention. And when you miss it, you miss out. So it's not everything that requires noise or laugh or laughter. To the east. And you need to put that declination into account in order to know how to navigate. So, and we did how we can know the true bearings for angle of declination. And I told you angle of declination is also known as angle of variation. Abi? And from there we did some calculations. I told you when the directions are the same, in order to get the true bearing, you had. If the directions are different, you subtract. And we dealt with that. Then after that, I talked about the angle of dip, or also known as angle of inclination. And the angle of inclination, we said it at the equator, that is 0 degree. Then at the pole, it is 90 degree. And these were questions they can ask you. Now, all of the things we have been learning so far, we want to apply them. How is this fan working is what we want to see now. How is your electricity generated into the fan working? Mechanical energy. That's what we want to talk about now. How is it that your electric blender at home works, or the soft juicer that brings out the orange juice, grape juice that you use at home? For all of you that used to do fruit juice, and you put it in a juice box, and you bring it to school for sodium tomorrow. So, how does that machine operate? Your electric blender, how does it rotate? Then all those blender and the fan, how do they work? That is what we want to talk about. So the basics of this is that you need to know, if you place a magnet on the floor and you place another magnet close to it, this is just a wire. I said it that according to Hosted, a wire that is carrying currents can generate a magnetic field around it. This is just a wire. It's not a magnet. But it itself behaves like a magnet for the fact that current is just flowing. And that was tested or experimented by Hosted, Fisier play mode. So now, if I bring a magnet so if I bring a magnet close to a wire, just a wire that is carrying current, and this magnet experience either repulsive or attractive force, how did that happen? This is just a wire, and this is magnets. I'm bringing another wire. Current is also flowing in this wire. You remember, this one has produced a magnetic field. This one will also produce a magnetic field. And at the end of the day, the field produced by this one and the field produced by this one, there will be an interaction. Either a repulsive interaction or an attractive interaction. That is it. Just the same way magnets. Why is this magnet influencing this magnet? It's because they are both in each other's field. So you are in my field, I am in your field. So depending on how they come together, they can either repel or attract. Same thing here. This wire has generated a field. It represents magnetic field with capital B. This wire has also generated a field we represent with capital B. Let's call the current that is flowing in this guy, let's call it I2 and call this B2. The current flowing in this one, let's call it I1 and call this B1. The length of this wire, let's call it L1. This wire is going to experience a force, and that force is going to be BIL sine theta. I will show you how we got this theta, depending on the angle of inclination for the wire. Now, apparently, for this force to be maximum, we always want this theta to be 90 degrees, to be perpendicular to the field. But for explanation's sake, this wire, this magnet, being in the field of this magnet, experiences a force. This magnet also being in the field of this wire experiences a force too. So now, this wire too, being in the field of this wire, is going to experience a force, which can either be attractive or repulsive. But now, how do you know the force? If it is going to be attractive or repulsive, that's what we want to talk about. And in order to know the force, if it is going to be attractive or repulsive, so to determine the force on a current carrying conductor, what is that current carrying conductor? This wire, Abi. Now, it's going to experience a force because it is placed in a magnetic field. So don't look at the topic that is very long and you'll be confused. We are just saying that this wire now is placed in a field of this wire. Then this wire will experience a force as a result of being placed in the field of this wire. And that is what we want to study. So how is that force analyzed? How do you know that force? The force is going to be determined by what we call the Fleming's left-hand rule. Fleming's left-hand rule. So this wire is already in the field of this wire now. Then what force will it experience? So let's look at the analysis. This is wire 1. Wire 1 has field like this. That field is B1. The current is I1. Then the length of the wire, let's call it L1. Now, putting all those asterisks there, I want to believe that you all know what I'm doing. Yes. Except you were not in class on Saturday. That's when you might not know. So now, wire 1 is already there. Then this is wire 2. And even if you were not in class, I think we still live streamed the class on Saturday. So, I to the Aye or La Josin. You can learn from anywhere. Life won't travel, God. So now, that is wire 2 carrying current I2. It has its own field, but I'm less concerned. So, this wire will experience a force. Will it be pulled towards this wire or it will be sent away? I will use Fleming's left-hand rule. So, Fleming's left-hand rule states that you are going to bring out your first 3 fingers like this from your thumb, the second finger, the middle finger. You bring the 3 fingers out and you make sure that the 3 fingers are held mutually perpendicular. Mutually perpendicular. That means this guy and this guy will be at 90 degrees to each other. This guy and this guy will also be at 90 degrees to each other. So everything, this guy and this guy too, everything will be at 90 degrees to each other. So just look at this. Let me do my own first, so you will do your own. All of you have to do it. And in case the day you want to write exam, and maybe the supervisor is not a science teacher, and he sees you doing like this in front of the system. There was, I think it was during the Moyin set last year, that their center, they collected their pencil, collected their calculator, everything that they brought, pencil and pen. And this guy said that, I will write, I will solve questions, I'm a science student. They said, no pencil is allowed. They said, and they didn't allow them to use pencil, so be prepared for the worst. JAMB already said that you can still be allowed to use pencil and all of those things, but the invigilator that day said no, you are not allowed to use pencil. And what will you do? So imagine that in the exam hall that day, you just look at your system, you are not doing like this. Then you now want to make it worse. By the time you start that, the invigilator will not talk. Akọ̀rọ̀ ayọ̀ síta, ẹ̀jẹ̀ bá mi wókùn. So that's why you have to pray that your invigilator is a science teacher, so that's even if the science teacher knows Fleming. So this wire 2 now, you now will use Fleming's left hand rule. This your thumb points in the direction of the force, and from the word thumb in Fleming's left hand rule, thumb, M means motion, and every time you have motion, you can talk about force. So when the 3 fingers are held mutually perpendicular, the thumb represents the force or the motion. This finger represents the field. This forefinger, the F there, can tell you that, oh, that points in the direction of the field. Then this second finger, so to say, the middle finger, represents the currents. So this represents the field. This represents the current. So if you want to determine the force experienced by a current carrying conductor in a magnetic field, you use Fleming's left-hand rule. So now, using my Fleming's left-hand rule, you will point this one in the direction of the current. You will point this one in the direction of the field. And you point this one in the direction of the force. So let me determine the force. This field that I have here, how is it going? And how will you describe the field? And we did all of these things, and we have been doing it from day one. It's going inside the board, Abi. So that means the moment you do your fingers like this finger that represents the field, you will point it inside the box. So you point it where it is going. Do you get that? Then where is the current going? Then this finger must point up, so you rotate your finger up. Alamoni. So now, where is my thumb pointing? Towards the left. So that means this guy would be attracted. That's the force. So yeah, let's do it again. This is your left hand. Hey, let me go more left hand there. This is your left hand. Then your finger coil. This one represents the field. So just keep these ones. Then this one. This one is pointing forward. This one is pointing down. Then this one to the side. So do it. Afikema no kakema buyon. Ordinary to do Fleming now you cannot do. This one out. This one out. This one out. Then this one down. Is that taking? Can you see? This one up. This one like this. Please, let's get it on time. We still have a lot of things to do. So yeah, try it. Hello, me know your what you. Get used to it. Be flexible. So this is it. So now yeah, let's do it. Where is the field going? Where is the current going? Then where is my thumb pointing? Oh yeah, check that. Can you see now? Yes. So that means that this wire will experience a force of pull. So your field is inside because the body is inside, Abi. Your current is up, so this points up. Then where is this one pointing to? Left. So that means the force is to the left. Please, is that taking? Oh yeah, do this yourself. So that means that note something. Look at these currents and look at these currents. You can see that they are both moving in the same direction. So when they move in the same direction, you will experience attractive force. So you don't even need the stories. But you need to know because they can just set up something for you. If there's any question online, you can ask. So now note this again. Everybody, look at this. So you will tell me the direction of the force. So this is B1. The field is due to B1, I1, L1, whatever, wire 1, wire 2. So this is I2. So what force will I2 experience due to the field of B2? The field is still inside Abi, but now the current is downward. So then your thumb is pointing this way. So that means we will repel the wire. Before you try this at home, please say that parental guidance apply. Don't let your mommy call me tomorrow and say, so John, ṣé nǹkan tí mo ní kẹ́ sọ ọmọ mi dà lélẹ̀? Physics là ń ṣe o. Now, to those of you that didn't understand, let's repeat it. Just point out your fingers. Just do them like this. This is it. This one, point it out. This one is still straight. Then this one up. Just curve this, remove these two. So one is up, one is this way, one. There's no way you can do it that. So it has to be up, forward, right. Just like that. Yes, that's it. That's it. So now, where is this one pointing to? Field, Abi, and the field is inside. So this one is pointing inside for this. Where is your current going? So this one has to point up, not down. This field is still inside. This is up. Then where is this pointing to now? Left. If you try this now, you see that your thumb will point in the other direction. Please. Is that okay now? So that is what you need to know in this aspect. Now, please listen. Anytime you see that the two wires, their currents are in the same direction, just know it is attraction. Anytime the currents are in opposite direction, it is what? Repulsion. You can see that book is interesting if you know what you are doing. Where's the duster? You can imagine you understanding how your fan operates. So now, that is theoretical. So quantitatively now, you can calculate this force. And how do you calculate the force? The force is going to be equal to BIL sine theta. That is going to be due to the field of magnetic field of wire 1, the current flowing in wire 2, the length of wire 2, then the force experienced by wire 2 as a result of wire 1 is equal to BIL sine theta. So they will give you the length of the wire, they give you the field. Another thing is that you remember when we produced the field, we said the field always go in a concentric manner, like in a circular manner. The field at a point in a wire is given as mu naught I over 2 pi r. R is the distance to the wire. That's the distance to that point. So I is the current that is flowing. So just know that B2 is going to be mu naught I2 over 2 pi r. All these ones are constant. So that tells you something. The force is going to be greater if the field is greater. Abi? If the current is high, the force will be high. And if the length of the wire in the coil in that field is much, then the force is also going to be high. Then theta also determines if the force will be high. If it is perpendicular, that means theta will be 90 degrees. Abi? Sin 90 is what? 1. That means that the force will be maximum. If they are parallel to each other, that means the angle will be 0. And sin 0 is 0. That means there will be no force. So everything we did was a perpendicular thing. So imagine this wire is not in this field. This wire is parallel. It's like this. It's not in the field. It won't experience any force. Or it just goes inside the same way the field goes. It won't experience a force because they are parallel to each other. So imagine this fan is working and I throw a marker under the fan like this. But you know, sometimes I can throw it perpendicularly to the rotation of the fan and the fan will strike it. Something like that. Look away. Don't sleep. So now, let me introduce this into this. So I can say the force experienced by wire 2 as a result of the field of wire 1 is going to be B2, which is mu naught. Mu naught is called permeability of free space. I2 over 2 pi r multiplied by, sorry, is this I2? This is supposed to be I1. You know, it is wire 1 that created the field. So I1, this is supposed to be I1. So B1 is equal to mu naught I1 over 2 pi r, which is what you have here. Do we get that? So multiply by I2, multiply by L2, then multiply by sin theta. So in some questions, they can say you should calculate the force per unit length. And that is going to be mu naught I1, I2, sin theta all over 2 pi r. So these formulas are important. So the common questions you see at this level is just based on this formula at this level. So what are the things to note? Don't sleep. You people should not be sleeping. You should maintain your sleep routine. Maintain your sleep routine. You did not sleep overnight. You can read till like 1 o'clock, 2 o'clock. Then you go and sleep. At least if you sleep from 2 to 5 or 2 to 6, it's okay. That's 4 hours. It's okay. Provided those on 2 soon be 2 hours. If you add that 4 plus 2, that's 6 hours already. So which is okay for 24 hours. But out of 24, if you sleep 12 hours at your youthful age, you sleep. You know, I used to tell you, if you sleep 12 hours out of 24 hours, that means if you are 60 years, you have slept for 30 years. So you have only lived 30 years. You see how useless that can be. So if you like, I like to sleep, no problem. Sleep. So please maintain your body very well. Immediately after the class, if you are the type, that's my own nature. That's what I'm saying. If I go for class or I go for anything, then I get back to my room. I can sleep 1 hour in the afternoon. I can sleep 2 hours just to relax. Then immediately I wake up, I can pick my books and read till next morning. I have to go and force myself to sleep. So that's how I used to do it. That 2 hours, that midnight. But if I now want to sleep, let me go and sleep around 4. Let's say I sleep 4, 4, 5, 6. I'm okay, I'll wake up again. But if I do not sleep that 4, 5, if I like, I should sleep from 9 till morning. And if I sleep from 9 till 4, and I wake up 4 to start doing things, during the day I'll be feeling weak. My own sleep between that 4 and 5, I don't know. There's something attached to it. So if I sleep within that 4, 5, 6, even if I have not slept for 24 hours, but that 2 hours, I will be okay for the rest of the day. So, but it depends on you. That's what me I've noticed for a while in my sleep routine, in my sleep cycle. So if you know you can sleep, and if I do not sleep in the afternoon, I can't really go a long night. If I do not sleep like 1 hour or 2 hours in the afternoon, I can't go long night. Highest is I'll read till like 12 and I'll go and sleep. But if I want to read and stay active till like 3 o'clock at least, I can sleep like 1 hour in the day. Then I can start reading from like 4 to like 3 midnight. I'll be okay. So, please, don't now come to class and start sleeping. Is Mr. Felix around? So now, this is the formula you need to know for that. Before I now talk about this, let's move on. You should know that they can ask you, and this is common sense, if the field and the wire and the whatever, they are parallel to each other, what will be the force? So note, the field, the currents, the length, whatever it is, if they are parallel, parallel means that theta is going to be 0 degree. And if theta is 0 degree, that is, F is going to be what? 0. Your force is going to be 0 because sine 0 is going to be what? 0. And everything will be 0. But if you want it, B, I, L, if they are perpendicular, then the force is going to be maximum. So the force will be maximum if they are perpendicular to each other. So can we move on? So the next thing you want to know is this. The force on a moving charge entering a magnetic field. You have a charge. Please, is there a problem here? There should be no problem. It's not so hard. The force on a moving charge entering a magnetic field. When a charge enters a magnetic field, the charge experiences a force. This application, you might know, this one, the application we are going to see soon when I start talking about electric motors and galvanometer and the likes. But this one I'm about to talk about, you might not really be able to think about the application. But quickly, let's see how it works. When you have a moving charge, a charge enters a magnetic field. That charge is going to experience a force too. And the force experienced by that charge is also going to be determined by your Fleming's left-hand rule. We are still going to do Fleming's right-hand rule. So now, I said force on a charge, on a moving charge. Force on a moving charge in a magnetic field. Force on a moving charge in a magnetic field. So you have a magnetic field like this, like this, like this, like this. So there are conditions to this. The field must be uniform. The field must be uniform, and the charge or the velocity The force and the field must also be perpendicular. The field has to be uniform, the charge, the velocity, and the force should also be perpendicular. So, mo ti rò pé ẹni wálé ni ẹ ti lè wọlé ẹ má wọrí mo mọ̀ pé yà ti mọ yín lára bọ̀ ẹ má wọrí ẹ wọlé èmi sọ fún yín ẹ sọ pé ẹ máa nà wọ́n kò sí wàhálà all personal. If not because the time is 2-3, I would have said that Man U would have won 3-2. But the time is 2-3, and only Arsenal people can relate. You people did not see that Emmanuel have gone lame since yesterday. Ọwọ́ ìyá ti bà. Wọ́n lù bí omi ẹ̀wà ní ojú àwọn èèyàn wọn. So, let me round it up. When the charge enters a field, please listen. There is a charge, but obviously we always treat this as a positive charge because in your exam, you will see negative charge. I will tell you negative, so you need to note. Now, when this charge enters this field, it's going to experience a force. Then when you use your Fleming's left-hand rule to determine the force, the field is inside. This represents the direction of the charge. Then this represents the force. So as this charge is entering, it's going to experience a force. In what direction will the force go? You can see that the field is inside, but the charge is moving to the right. So this one will point to the right. Do you get that? But where is my thumb pointing to? Up. That means that when the charge enters, so let me make the charge to really enter properly. The charge is going to experience a force that will hit it and pull it more like a deflection. So it will now move in this direction. Now that it's moving in this direction, what will you experience again? You do your left hand again. Now, your thumb will point this way because this is the direction of the charge now. The field is still inside. Then it's pointing this way. Then it will also move out like this. You also do your hand again. It's coming down. So you notice something. If you continue, this guy will continue to be going up, down, up, down, up, down, like in a spiral manner. It will continue to move like that. Inside, up, back, back. So they can now ask you, in the first scenario now, I told you, in what direction will the charge move? Up, Abby. That's what you will say. It's when you put your hand, you will see that it will move up. Then just show the direction that it's moving up. Now, if they now told you, or what I did here, I just put negative. If you see that this sign is negative, that means you will pick opposite of your answer. If you put your hand now, where is this guy moving to from here now? Up, Abby. Then, for the fact that is negative, you will pick down. But if anyone you do with your left hand is always for positive. But negative move in opposite direction to positive. So, whatever you do, you are doing for positive. But if they indicate negative here, you have to pick positive as your answer. I mean, you have to pick opposite as your answer. So that's that. So how do you determine the force? The force is given as the field that it enters multiplied by the charge that is entering multiplied by the speed at which it enters, then at angle of sine theta. So that's another important formula. This formula and this formula, they are important for our class. So on Wednesday, we'll deal with the application properly. Then on Saturday, we should end everything on magnetism. So we can go to AC circuits next week. So Bye bye.